Hello! Today we are talking about such a concept as rest of the body, or rather its equilibrium. And in dynamics, we have already met with such a phenomenon when the body is at rest. And let's remember how the conditions of this state of the body are determined. Now let me remind you that the state of rest is the absence of any velocity of this object, and this condition is fulfilled if the sum of all forces acting on the body is zero. Well, in this case, it is clear that the situation is possible if nothing acts on the body at all. In order to do that, of course, we have to find a certain place very far away from any objects in the cosmos, and if we ignore, say, their gravitational pull, we can say that nothing is actually acting on the body. Then the body can be at rest if there are no forces. On Earth, of course, we can't reason in that way, so we necessarily say that there must be compensation for all the forces acting on this object. But as it turns out, this condition is not sufficient for the body to be at rest, because we are thus talking about the absence of translational motion. So the action of the force, exactly the uncompensated force, will cause a certain acceleration, and it will be a linear acceleration, translational acceleration, which will cause this motion. But we remember very well that we have another kind of motion, which is called rotational motion. And here the question arises, how to make the body in the end move neither progressively nor rotationally. For that, of course, there's another condition, which is that there's no angular velocity. Angular velocity. And so here we must remember what causes angular velocity. This quantity is called the momentum of forces, and here accordingly we get a similar condition, that is, the resultant moment of forces acting on this object must also be zero. I will designate the moment as a vector quantity because it also has its own direction, and this direction we will now learn how it will be determined. But the most important thing is to look at specific problems. How all the moments are summed up and what is the result of their summation. If the total moment is zero, then you will get the equilibrium of this object. If it is not zero, then this object will start to move with acceleration, i.e. rotate with acceleration. So, now the question is how to calculate the resultant torque with respect to its direction, that is, where it's ultimately directed. Let's look at a case where we have a certain part that's fixed at point O, and so it can rotate in the vertical plane. And let's say we're acting at a certain angle to this part, and let that force be F1. And for example, this force is at an angle to the axis of the part, Tt1. In this case, how do we calculate the moment of this force? In this case, let's remember that the moment is directly the product of the force acting on a given object by its shoulder. We call the shoulder of the force the perpendicular, which is lowered from the point of rotation to the line of action of the force. We see here that the force is at a certain angle, and we can calculate the momentum of the force in two ways. So either you and I draw the line of action of the force, and then we draw a perpendicular from the pivot point, and we get the leverage, d1. We will find the length of this perpendicular on the basis of the obtained triangle, in which we see that the vertical angles are as follows, is θ1. The hypotenuse of the resulting right triangle is, let's say, the length of the rod itself, and then we get the moment of this force. This is the product of the force itself, of the force F1, by its arm d1. And here we see that the arm d1 is the opposing cathetus for the angle θ1. We can calculate it through the sine of this angle. Then we get the product of F1 over L and over the sine of the angle θ1. This is exactly the situation when you and I can break some segments into certain components and find their components. We can consider the second way of solving such a problem, i.e. to break the given force into its components, i.e. into its projections, and consider one of them which is located perpendicular to the given rod, i.e. directly acting at right angles to its length. In this case, this component will be the projection of the force. Let's write it as F1, perpendicularly acting. And here it turns out that we will also find this force through the angle θ1. We have it in this triangle here. And it is also the opposite cathetus for the angle θ1. So it turns out that we multiply also now the total arm L by the magnitude of the given force. Then the given moment of force we will write as L multiplied by F1, perpendicular to the components. And what is the perpendicular component? It is the product of the hypotenuse by the sine of the angle. Then we get L times F1 times the sine of F1, θ1. As you and I can see, the expressions are exactly the same. This shows once again that you can find the moments in different ways. It is up to you to choose this method that you are more comfortable with. But as you and I understand, what we are talking about here is that we want this rod to be at rest. What do we need to do that? To do this, of course, we need to balance this force with another force, specifically another moment. That is, you have to create a certain action of some other force that will prevent this rod from rotating. So here again, at some point we can apply a force F2 so that we get the rest of this body. Let's show in the figure. This drawing already taking into account that we have a second force. So we have a force F1 somehow. And then, for example, somewhere in this point, let there be a force F2. In this case, this force will also be calculated on the basis of certain relations. That is, we must know at what point exactly it is applied. Also calculate its momentum. Well, let's say I just drop down perpendicularly from the point of rotation O to the line of action of this force. This is the magnitude of the arm D2. And then you and I have two of these moments. Let's draw again the hour hand, that is its motion. And let's see the rotation in which these moments are created. That is where they rotate this body. F1 can be seen. It rotates the body counterclockwise because our clockwise hand goes that way. The force F1 pushes the body in the other direction. Therefore, its momentum will be located with a plus sign. And therefore, the force that rotates the body clockwise, it rotates it with negative momentum. And we end up with the difference of the two moments. So in order to fulfill the equilibrium of this body, this difference must be equal to 0. That is, these moments must be equal in modulus and opposite in direction. Actually, that's what we've got. Here there is one nuance. When we are talking about the directions of moments, then how to correctly determine the direction of the moment of force. Here, we show it conditionally enough and compare them with the clockwise motion. In fact, the momentum vector is located in a plane perpendicular to the figure itself. In order to determine the direction of the momentum of force F1, we have to use the four fingers of our right hand. Start moving in the direction that the force is rotating. That is, in this case, it rotates the body counterclockwise. We then, with the four fingers, make an outreach in that direction and the thumb points towards us. So the direction of the momentum F1, we can show you this way. The point toward us shows the vector that is facing us from the figure. Yeah, and we see that for the force F2, everything will be in the opposite direction. So we have four fingers pointing in the direction of the force. And the thumb is, in this case, pointing into the figure. So the momentum vector θ2 will be positioned like this. We show a cross in this case. This is a conventional notation which is accepted and which we use when it is necessary to show the vector that lies in the plane perpendicular to the figure. Thus we have obtained the condition under which the body can be at rest. That is, there is no rotational motion. This is the compensation of the moments of force. Of course, there can be more such moments. That is, there can be 2, 3, or 10. And the most important thing is to correctly determine their direction and their magnitudes. If you do everything correctly, you will most likely have one unknown in this equation, which will then need to be calculated. Another very important issue that is touched upon in the topic of statics of bodies, This is such a concept as the center of mass of various objects. This point is very important in the theory of equilibrium, and it's fundamental when we're talking about the balance of figures. Let us consider such a situation when we have, for example, some log which has the shape of a truncated cone. Let's say we cut the tree down, and we've cut off the top of the tree. Accordingly, here we have a thicker base. And this tree will have the shape of a truncated cone. This is our cross-sectional drawing. As you and I understand, the center of mass of this object will be located in a place that is closer to the concentration of mass after all. And as we realize, the concentration of mass sits right here in the thicker part. So theoretically, we can assume that the point of the center of mass is located here. Let's denote this point by the letter C. What is the specificity of this point? If we can somehow launch this tree so that it starts to rotate, which is to throw it by one end, the only point that will not rotate, that is relative to which this object will start to rotate, is the center of mass. So we have, for example, a knife flying which rotates relative to this point, which we throw to the target, and it's just moving along the curve of some sort of parabola, or other objects that can start rotating in flight. Point C will be the only point that in this case moves progressively, i.e. without rotating. And then the question arises, and how to determine this position of the point on the body? When we meet with such a problem, it is of course a little bit beyond the school course, because here we have to go to the side of higher mathematics. But we can consider simpler situations where we have an object that consists of bodies that have specific positions on some axis. Let's say we have a gondol that's made up of 3 balls, and these balls each have a different mass. Let's say this one has a mass of m1, this ball has a mass of m2, and this ball has mass m3. We don't know what these masses are yet. It's a convention. And let's assume that these balls, let's assume that they are equidistant from each other, that is, the length of the segments between them will also be L. How in this case to determine the position of the center of mass of such a system? That is, at what point can we place a support for this system to be in equilibrium? For this purpose, there is a special formula which we will write down now. And this formula is something we can trade off in different dimensions. That is, now we see that all masses are located on one line. That is, we are now working in a one-dimensional space. Let's say along the x-axis, and calculate the coordinate of the center of mass along the x-axis. It is clear that here you can also add a second coordinate, i.e. this figure is already located in the plane. Then you will calculate the same thing, but by another coordinate. Therefore, this formula is universal. So, what is the coordinate of the center of mass on a given axis? First, of course, we must understand what to choose as 0, that is, from where we will consider the origin of reference. Let's say it's the first ball, that's position 0. Then with respect to this point, the position of the center of mass will be defined as follows. It is the product of the mass of the body by its coordinate, and we sum all the corresponding summons. As many of these objects as you have, that's how many of these summons you have to write down here. And at the bottom, we divide by the total mass of the whole system that you have here. Let's say we have 3 objects. So I've written 3 summons here at the top and bottom. Thus, you, having calculated this parameter, will already be able to show at what point this center of equilibrium will be located. This formula is ready to go, so you can work with it. Try it out. To try it out with specific examples. So today we have considered the topic of equilibrium of solids, and in practice we will apply these laws in order to consolidate our knowledge. That's all for now. Goodbye, everyone.